All right, so this webinar, and I think I mentioned it is being recorded, so you will be able to rewatch it if you like. It's broken up into 7 sections. They're fairly short sections, and what you will get, hopefully, when you leave here is an appreciation for the complexity of surgery suites, you know, the difficulties and the challenges in air conditioning a surgery suite, and how we do that with a piece of DX equipment. Okay, what functions and features and controls are required in a piece of DX equipment to meet our design objective in a surgery suite. Okay, so section 1, we're just going to talk a little bit about surgery suites in general. So, you know, I had this misconception that a surgery suite is just the OR, but it actually includes the adjoining rooms as well. And I tried to get educated on all the different types of adjoining rooms. There's a lot of them, okay? And I'm not an expert on that. But some of them are like the recovery room and the scrub room. So all these rooms that touch the OR, people travel back and forth, all have the same kind of requirements for temperature, humidity, and cleanliness and things like that. So the average operating room is 600 square feet today. Apparently it used to be 4, now it's bigger. There's a lot more stuff in there. This is a typical operating room. You got a lot of people in there, a lot of lights, maybe some extra filtration. There's a lot of stuff going on in these small spaces. And I would guess like an operating room like this would probably be about 5 or 6 tons of AC just for this room. So I took this quote from the Association of Professional and Infectious Control Guide of 2018, which says air quality, airflow, air pressure, temperature, and humidity in the rooms that make up the surgery suite are interrelated and all are tied into the function and design of the HVAC system. So air quality, airflow, pressure, temperature, humidity, and also I would add like cleanliness. There's a lot of stuff going on in these small rooms to make sure that we cool and dehumidify the room properly. There is an ASHRAE standard 170. I believe the most current version is 2017 that talks about healthcare applications. The main objective, is to reduce SSI, which is surgical suite infections, which is a really, really big problem in these operating rooms. So the design of the HVAC system falls in line directly with that objective. We have high air changes per hour, which we'll talk about in a minute. Low temperature, low humidity requirements. The low humidity is obviously to prevent condensation, which is a huge no-no. You definitely don't want any condensation in these rooms. Cooler temperatures, good for the doctors. It prevents them from sweating. It's also very good for the patients, I found out. I read that yesterday. I didn't know that. So it has to be under positive pressure to adjacent spaces, and high level of filtrations are required, MERG 7, 14, and sometimes HEPA. Okay, the air source in the OR must be free as possible from microorganisms, which plays in line with the filtration and maybe UV lights into the equipment. And for operating rooms, a minimum of 20 air changes per hour total, 4 of which come from the outside air. So I put all this on here just to, reiterate the complexity and all the things that need to be taken into account with surgery suites. Okay, so what we typically see, and I see these temperatures all over the map. I think, in my opinion, 60 to 68 is probably the most common range we see today as far as temperature in the room. Some are a little colder. Chris just talked about an application he's working on that's 57. So when I give these values, I'm kind of just giving like general rules of thumb based on what I typically see. And then 20 to 60% R8. So a lot cooler and a lot drier than we would normally see in a typical HVAC, at least DX application. So if we take these temperatures and humidities, like as a equipment selector, if an engineer comes to me and says, I need to meet these ranges of temperature and humidity, what do you got for me? The first thing I like to do is plot it out on a site chart to kind of see where we're at as far as the dew point goes. So if we look at 60 degrees, dryball, draw a line here. 68 wet bulb, draw a line there, and then I fill in the 20% RH and the 50% RH, which is here, and I kind of shade this in. And this gives me an idea of the top level dew point in the space and the bottom level, which then I could kind of think about, okay, this rules out standard DX equipment, or this is obviously in the desiccant area. And this is kind of what I'm doing here with this exercise. So in this case, the bottom range of those temperatures and humidity levels is 20, and the top is 49. Okay, so we have, you know, in a broad general sense, 3 options when we're choosing our HVAC equipment, right? DX, chill water, and desiccant. So we talked about surgery suites. Now we're going to go on to section 2 and talk a little bit about what, as designers, HVAC suppliers, sales guys, what equipment do we have that will meet, you know, that criteria. So what I like to do when I'm thinking about equipment, when someone comes to me with an application, especially when it's in these lower dew points, is I like to put that on a site chart as well. So my kind of first look at this from a bird's eye view is 55-degree dew point. So anything over 55-degree dew point, I could do that with either standard DX, what I call specialty DX, which I will define in a few slides here, or chilled water. So anything over 55-degree dew point, we can generally take care of it with those 3, any of those 3 options. The next area I like to look at is kind of the bottom of what DX can do. And this is, again, generally speaking, okay? This is not a hard and fast rule. It depends on the equipment supplier, who you're working with, and all kinds of different factors. Where you are in the country even could affect that. So in this range, from 55 to 42, that kind of, to me, knocks out the standard DX, okay? It puts me in a special DX or a chill water, especially if I'm trying to control temperature and humidity over all load conditions, okay? And then anything below 42-degree dew point, I consider that a glycol system or an active desiccant system. And then there's some gray area of hybrids of specialty DX and active desiccant, which I think is a great solution for, you know, these kind of on the edge, is it okay to use DX applications? You know, there's small desiccant products which work very well in addition to packaged DX or split system DX equipment. And you know, if you've been around a while, you know there's pros and cons and engineering trade-offs to any of these systems. You know, the packaged DX or split system is generally your lowest first cost. There's some efficiency savings there, especially when you're in applications that require a lot of reheat, because you get a lot of free reheat off the hot gas. Chill water has a little more flexibility, but is more expensive and obviously more maintenance. Desiccants are great when you need them, but they're not great when you don't need them because they're expensive. So I've done desiccant jobs. I think the lowest dew point I did was in Tallahassee, and that I think was minus 50 degrees and a minus 50 dew point in a lithium ion battery facility. So they're fantastic when you need them. They really do a great job at the extremely low dew points. So what are other, we're talking about surgery suites here, but as I was doing this presentation, I was thinking, well, all this stuff that I'm going to talk about in the DX equipment really could apply to any low dew point scenario. And by low dew point, I'm talking like in the low 40s-ish. There's lots of labs we do that qualify for low dew point, pharmacies, some archival storage facilities, and some manufacturing facilities. So any of these type of buildings or facilities that have low temperature, low humidity requirements will fall into the category of this presentation. I could change the name of this presentation to low dew point labs, and really from the equipment side, there's not much of a difference. So I wanted to point that out in case you're thinking, well, I don't do a lot of surgery suites, but this has a lot of applications elsewhere. Okay, so I use the term specialty DX, which is, you know, I don't know that that's really an industry term. That might be just a Tony term. A lot of people will call them custom DX units. I don't really like the word custom because custom to me implies you design it once, you make one of them, and then that's a custom unit. So to me, in my head, semi-custom, maybe. Highly configurable, yes. I like the word specialty because they are designed to do a special application, okay? Which in this case would be low dew point, temperature and humidity control, overall load conditions. And that leads me into this slide, which is, so the DX, specialty DX equipment is designed to go from extreme part load all the way to full load. So in that operating room we looked at earlier, it may be 6 tons on a full load day, but it may only be 1 ton when it's not loaded or at a part load day. And you need to have that range in the equipment. And more importantly, you need to have the ability to modulate everywhere in between it. Okay, doing full load is real easy with DX equipment. It's the part load where is the challenge and where we need to have everything in the unit that we can modulate, we should have the ability to modulate it. And of course, want to mention controls. The controls need to be specific to the application you're working on. So if you're controlling the temperature and humidity in the space, the controller needs to be able to read that and effectively modulate the components of the unit to achieve that design objective effectively, efficiently, and consistently, okay? And we do that sometimes with application-specific controllers, configurable controllers, or sometimes even custom controllers. So if we kind of step back and look at this operating room, this is my fake operating room I'm drawing on a site chart. And we add a temperature and humidity sensor in there. Okay, so we're going to control temperature and humidity in the OR. And let's say for this example, we're doing 65 degrees and 50% RH. Okay, so I'm going to draw this out. 65 degrees, 50% RH is right here. If we draw this line here, this will represent the dew point set point of the space. Okay, so anything above the dew point, what we typically do in these applications is we look at the space, temperature and humidity, we calculate the dew point. Anything above the dew point set point, in this case 45, we go into dehumidification mode, which is a very cold coil and then reheat, and we're going to talk about that a little bit later. If we're anything below the dew point set point, then we have to make a choice whether we're going to heat the air or cool the air. Okay, so obviously if we're below the dew point set point and we're in this range here in the space, we're going to heat the air up to achieve the space conditions of 65. If we're to the right and below the dew point set point, so if we're in this quadrant here, we would cool the air down to make sure we're cool in the space. And those are the 3 primary sequences that's going on here. In addition to that, we have to maintain a positive pressure in the space to the adjacent spaces. We have to bring a lot of OA into the operating room. You know, relative to the size, it's a pretty heavy OA load. And the OA load is constantly changing because you got cool, rainy days, part load, and then you got hot, sunny days, full load. And then you got all this stuff going on in space. You got people, you got lights, you got filtration units putting heat in there, you've got sterile equipment. So there's a ton of stuff going on in this little room. So specialty DX equipment that has the features we're going to go over will make sure we can do all this stuff. So this is kind of, I like to look at this just to show people like there's a lot of stuff going on that we need to make sure we take care of, and standard DX equipment just cannot do all this stuff. All right, so modulation, we talked about that before. What are we going to modulate? We're going to modulate the cooling, the heating, and the hot gas reheat in the dehumidification mode. Those are the 3 primary things we're going to modulate. Okay, so now I'm moving into section 3, where I'm going to briefly go over the refrigeration cycle, because I think, you know, if we're going to understand the modulation of the compressor and the hot gas reheat, it's really important to go back to the basics and understand the refrigeration cycle. This might be a review for a lot of people. For some people, it might be new information. Okay, so What's going on this slide is everything in this brown box represents an air conditioning unit. It could be a packed unit, it could be a split system, doesn't really matter. You have the space here, so the air is coming out of the system, going into the space, absorbing any heat or humidity, coming back into your AC system through your evaporator coil. So this is where the air goes, but we're going to focus here on the refrigeration cycle, which is right here. Okay. So every refrigeration cycle, from a water fountain to a 2,000-ton centrifugal chiller, has four basic components. We're going to go over those real quick. One is the compressor. Two is the condenser. Three is the expansion valve, or TXV, thermal expansion valve, or pressure drop device. And four is the evaporator coil. Okay, so what happens is the gas comes into the compressor as a low temperature, low pressure gas. It gets compressed and it gets heated and pressure gets added to it. So it gets heated to about 140 degrees, comes out of the compressor, goes into the condenser, which now is able to reject the heat to the relatively cool atmosphere and condense it into a liquid. So let's say it's about 100 degrees, and these are general temperatures and pressures for 410A. These are just average temperatures. They could be different than this for sure. So 100-degree liquid comes back around to your pressure drop or expansion device, goes through there, and when it does, it cools off, and it goes to the low side of the system, let's say 42 degrees, goes through your evaporator coil, and what happens is this air boils off the liquid into a gas. And that's where really the whole air conditioning refrigeration effect takes place, is right there. So the ability to change state from a liquid to a gas, that's the whole purpose of the refrigeration cycle. So it absorbs the heat, boils off, it leaves approximately the same temperature, just a different state, and then goes into the compressor. Okay? So that's your basic refrigeration cycle, 4 components, pretty common in all refrigeration cycles. To add some pressures here, and again, this is for 410A, the high side's about 375, low side's about 120, just to kind of give you an idea of what pressures we're dealing with. Okay, so the limit, like when we were talking before about the cutoff of where we look at DX and then when we switch like to glycol in a desiccant system, it's totally based on this right here, which is the suction temperature. Okay, you can only go so low before you start freezing the coil, freezing up the system, causing low oil return problems. That's the limiting factor with DX. And the approach from this number to the leaving air temperature is usually in the 8 to 12 degree range, something like that. So 42 degree suction would get you 50 in the low 50s, leaving air off the coil. Okay, so low suction is the big enemy of DX systems, okay? And what happens when you have low suction is, as this heat load drops, let me back up. Let's assume this is a 5-ton compressor and you have a 5-ton refrigeration system here. At full load, you have enough heat to boil off the refrigerant and bring the gas back to the compressor. As this load drops, you put less heat into the system, and this suction temperature will continue to drop and drop and drop, because the compressor is always running at 100% in a standard DX piece of equipment. So as this suction temperature drops, the equipment has to make the choice whether to turn the system off or to keep going and freeze up. And generally, it's going to turn itself off with the safeties. The problem is if you're dehumidifying or doing an application like a surgery suite, you can't turn the unit off because you have to continuously be dehumidifying. Okay, so what happens at low suction? If it runs amok, this is an extreme example of something I just pulled off the internet. Obviously, this compressor is running way past where it should. The safety has failed, and it's frozen the evaporator coil in the compressor. Okay, so this is what happens at extreme low suction. So to prevent that, what we used to use, and we still do on a limited basis today, is what's called hot gas bypass. So this diagram here shows the same refrigeration cycle as before. It's just drawn a little bit differently. You have your compressor, your condenser, your TXV, and your evaporator. So what happens in a hot gas bypass situation is, this is the compressor discharge, and if you remember, this gas is very hot. So what we do in a low temperature, low pressure situation is we take some of that gas and we inject it in the inlet of the evaporator. Oops. Sorry about that. Thus falsely loading the system. So it's a way to keep your system running at low load conditions without freezing it up. So it looks at the temperature and pressure here at the inlet. As that drops, translates back to the valve. The lower pressure allows the valve to open and let the gas flow through into the evaporator. Okay? It's really just kind of a mechanical device, doesn't have any controllability. It's not looking at, the leaving air temperature and adjusting or anything like that. So it's a pure mechanical freeze protection device which keeps your unit running. Hot gas bypass is kind of it's not very healthy for the system, right? It can cause overturn problems. It's extremely inefficient and kind of a big pain in the butt for HVAC systems. But it does work. And before we had modulating compressors, this is what we used. I show this slide because a lot of people get confused between hot gas bypass and hot gas reheat. And they might think that if I have a 5-ton unit with hot gas bypass, then I could control and modulate over all load conditions, and that's not really true. All right, so the next section is a better way. Now we're on section 4. So this leads into the modulating the compressor part of this presentation, which is really one of the main reasons why we could do this today very effectively and efficiently. We could not do it, 10, 15 years ago. This allows the unit to be basically like a hot water or chill water unit. So there's 2 modulating scrolls that are very popular today. Before I talk about those, I'm just going to talk about a scroll compressor in general, because a lot of people may not understand how they work. So this is a typical scroll compressor. You have a base with a vibration isolation. The motor is right back here in this can. Power inlets here. Power connections here. Your suction pipe would be piped up here. Suction gas comes into the compressor, gets compressed. Your high temperature, high pressure gas comes out the top, your discharge. And what this looks like internally, if you were to take this and open it up and take these plates out or scrolls, is this. And these 2 things kind of mesh together and rotate to compress the refrigerant down, and we're going to look at that in a minute. So one of them's a bottom one that moves, and this one's the top one that's fixed. Okay, so if we look at the top of this compressor, we take this can off, look at the top and look down, this is kind of what we'd see. So the gas is coming in here, and the blue color denotes it's a low temperature, low pressure gas. It goes through these ever decreasing chambers and gets forced out the top as a high pressure, high temperature gas. And okay, it worked. So this is kind of what it looks like visually, okay? And what's going on here is these chambers are ever decreasing, and it creates a seal at the touch points. So this gas right here is in this chamber, and it's sealed there, and it gets pushed to this chamber, et cetera, and it goes on, and it comes out as a hot gas. That's how a typical scroll compressor works. It's either on or it's off. Okay, so there's 2 common modulating compressor options today, the digital compressor and the variable speed compressor, and there's a lot of confusion about what the difference is between the 2, so I'm going to go over that real quick and give you the pros and cons of each in my humble opinion. So the digital compressor from the outside really doesn't look a whole lot different. So I'm just using the same photo. It is a little bit different, I believe, but you can't really tell much from the outside. It's also known by the names of variable capacity compressor, modulating scroll compressor, or VCC, variable, short for variable capacity compressor. So there's a couple different terms all describing the same thing. So if we were to look at a cutaway here, this is what we would see inside the scroll. And you could see every few seconds, the top plate lifts up and it goes down, lifts up and it goes down. So what's happening is when this plate is up, no compression is going on. It's only compressing when the plate is down. Okay, so this is how we modulate the capacity in a digital compressor. Important thing to note is the motor, it never changes the speed at all. So when it's pumping, it's always pumping full motor speed, full RPM. So it's engaged, disengaged, engaged, disengaged, etc. The method of control it uses is what's called a pulse width modulation method. And if you look here, here's two conditions. Let's say we're 50% loaded. What we do is we take a 15-second cycle and we break that up depending on the loading. We break that up into pumping and not pumping. Okay, so if you only need half capacity, you're pumping for 7.5 seconds and you're not pumping for 7.5 seconds. If you needed 80% of the capacity, you'd pump or engage the scrolls for 12 seconds and disengage them for 3 seconds. That's how it works. It's very simple, ingenious design as far as I'm concerned. It's really nice. This graph here is to show you the efficiency savings you would have with a digital compressor. So this is the percent of full load power versus your capacity. And you can see when you have an on-off compressor with hot gas bypass, that doesn't really change a whole lot. So like I said before, if you've got a 5-ton compressor, it's in hot gas bypass mode, it's pretty much using the full power the whole time. As opposed to the digital, if we look at the 50% capacity range here and go up, you're using about 60% of the full power. And that's because when it's disengaged, you're still using some of the power. That's why it's not a more direct relationship. So there's a huge energy savings here with the digital compressor. So here's some of the advantages of the digital versus the VFD compressor. So lower first cost, simple controls, talk about that in a second. This really is not very accurate how I put this under advantages because the VFD compressor is very precise as far as allowing us to control temperature and humidity. So that's a wash between the two. It does have a better modulation range than a digital compressor. So 10% of the compressor itself, it can modulate down to safely. And remember too, if you have multiple compressors in a unit, if you have 2 compressors in a unit, then you're down to 5% of the unit total capacity. And the oil return is very effective in these compressors. So the velocity of the refrigerant directly determines the ability of the system to push the oil back to the compressor. In this compressor, you're not changing the velocity because when it's pumping, it's always 100%. So you don't have that much concern as far as oil returns. The disadvantage, if there are any to this compressor, is it does have some acoustical characteristic when it engages and disengages. Whenever there's a noise like that in a system, it tends to be a little bit annoying. 99% of the time, it's not an issue. If you're putting it in a sound-sensitive area, make sure you talk to your rep if the equipment you're using has this compressor in it, just to make sure that there's no problems. The variable speed compressor is the other option, which is very popular today. You can see it is very similar as far as the compressor goes. It does have the extra VFD, which you need to modulate it. And it does require an electronic expansion valve, where the other one has just a regular mechanical expansion valve. Okay, so that's an extra device, extra couple devices needed here. It's also called a modulating scroll compressor, inverter compressor, VFD compressor. So the biggest difference here is, and this video shows it pretty well, is that the speed changes based on your loading. So as before, you're always at the same speed and you are engaging and disengaging the top scroll to determine your capacity. Here you actually change the speed of the motor. Okay, which is really nice. The scrolls don't engage or disengage. They're always compressing while the motor's spinning. It's just the speed of the spinning determines how much capacity you get. So some of the advantages, it is higher efficiency than the digital, so you get that. Precise control, again, the digital and this compressor have extremely precise temperature and humidity controls. One of the advantages over the digital is it is quieter, because it's slowing down. It doesn't have that engaging and disengaging aspect to it. The disadvantages versus the digital compressor does have a much higher first cost because there are some other pieces you need and a higher complexity, the VFD, electronic expansion valve. The modulation is 10 to 25%. I think it's more like 25% in most applications, so it doesn't modulate as low as I would like for these applications, but those are the disadvantages to this compressor. It's a very good compressor if applied properly. Some of the other disadvantages, like we talked about with the oil return, if you change the velocity, you have oil return considerations. So if you're running at extreme part load for a long time, the compressor actually has to go into what's called an oil boost mode, which is nice because it gets the oil back. But what it does is it'll run the compressors at 55% for 5 minutes. Every 2 hours, it is below 50% of the capacity. So, if you're trying to precisely control temperature and humidity, that could be an issue. So it's something to look at, and it could actually cause your coil to freeze up at low load conditions. So just be aware of those things. And I'm a big fan of both compressors if they're applied properly. Okay, so we talked about cooling. So moving on from section 4 to section 5, we'll talk about heat. This one's real short. It's pretty easy. And we're talking about here the primary heater in the unit, not hot gas reheat. We're going to talk about that in the next section, and then we're going to finish it up with 1 or 2 slides. So electric heat, gas heat, hot water, those are the 3 primary ones. I would say hot water is maybe, I've done 2 units in 20 years with hot water as far as having it as a heater in a DX piece of equipment, but it is an option. So electric heat, again, we want everything to be modulating. So SCR is a must in these applications, in my opinion. The great thing about SCR heat is it's pretty bulletproof and you get infinite turn down and precise control. Okay. Gas heat absolutely has to be modulating, in my opinion, in these applications. The good news is modulating gas heat is pretty standard in most specialty DX equipment these days, so it's usually not a problem. You want to check the turn down of the heat, okay? Common turn down ratios are 3 to 1, 5 to 1, and 10 to 1, and what that means is, like in a 10 to 1, you can go down to 10% of the capacity. So you want to check that delta T, take the full capacity, MBH of the heater, take the minimum, run it through your equation, check to see what your minimum delta T would be. If it's 5 degrees, it's probably not a problem. If it's 15 degrees, maybe you want to look at, using electric heat instead. But just be aware that that is something to check. Make sure it's modulating, and always check the turn down. Some people will actually do, in the northern climates, they'll do gas heat, and then they'll do an electric heater in the duct for just the extreme, precise turn down they need as a supplement on those days where they need it. So hot water, if you're going to do hot water as your primary heat source in the DX piece of equipment, make sure it's modulating and also check the turn down. Make sure you're designing the hot water coil so that it could turn down properly, it doesn't get into laminar flow situations and cause you no heat. All right, so cooling, heating. The last thing we're going to look at is the dehumidification sequence, and then there's only 1 or 2 slides left in section 7, so we're almost done. So the dehumidification sequence, kind of plotted this out on a cycle chart. Low dewpoint dehumidification, this would be what I call an extreme part load situation, because I want to show you the reheat and then some auxiliary reheat that may be required. So let's say we have a space at 70 degrees and 50% dew point. I didn't mean to click that yet. We have a space at 70 degrees, 50% dew point. Okay, that's our design objective. And let's say our mixed air temperature is 72, I don't know, 64, wherever that falls, something like that. Goes through your cooling coil, where it dehumidifies, cools the air. Then we're going to reheat this back up with modulating hot gas reheat. We're going to look at how that works in a second. You always get a little fan heat as well in your system. In some extreme situations, you will also need maybe a little bit backup electric heat or gas heat. And we use the primary heater in the unit as this backup. This only happens when you cannot pull enough heat out of the air to reheat. It's extremely rare, but it does happen on extreme cool, wet, rainy days when you got a lot of people in the space. These are the kind of situations where you might have this happen. So we always want to have an extra, just a little bit available of reheat for those situations. Okay. So let's talk about modulating hot gas reheat, which again is completely different than hot gas bypass. Okay, we go back to our refrigeration drawing. Okay, and let's say you have 45 degrees. Let's say you're in dehumidification mode. Okay, so you have a very cold coil. You have 45 degrees leaving the coil. At some point in any space, if you blow cold air in there and there's not enough load in there, you're going to overcool the space. Okay, so that's the sole purpose of hot gas reheat, is to temper that air, reheat it back up so you don't overcool the space, get a bunch of condensation, all that stuff in there. So how can we reheat this air? Well, we can use the primary heat source of the unit, or why don't we use some of this hot gas coming off the compressor that we normally would reject the heat to the condenser. So what we do is we add this three-way valve in here, take some of this gas, we route it through a reheat coil, which is downstream of the evaporator coil. Refrigerant comes back into the system, a little bit cool. Okay? And then let's say we're reheating up to 60 degrees. Totally arbitrary number, I'm just picking that as a point. Then you would also get some fan heat. And if you needed 60 degrees here and you couldn't get enough reheat, that's where your auxiliary heater would come in. I probably should dress this slide up and show that here. I'm going to do that on the next time I do it. But anyway, so that's where your auxiliary heat would come in if you can't get enough reheat here. And the reheat capacity is totally dependent on how much heat we're pulling out here. Okay? So I always like to ask this question: where does the dehumidification take place in this system? A lot of people believe that this is where you're dehumidifying, which is not correct. You're actually dehumidifying at the evaporator coil, because the coil is at a lower dew point than the air, and it's pulling the moisture out. This is only a sensible heat device. Just thought worth mentioning. All right, so section 7, we are almost done, and we're going to have a few minutes for questions, which is great. And again, we really do appreciate everybody joining us. So let's put all this stuff together real quick in the unit, in the specialized DX piece of equipment we're building with all the features to meet our design objective in the surgery suite or other low dew point applications. So digital or VFD compressor. I put multiple question mark because if you have the ability to do multiple compressors, it's probably better. Of course, we look at that on a design basis and make that determination. Modulating heating. So your primary heat source should always be modulating. Modulating hot gas reheat downstream of your cooling coil. It's a must for dehumidification. I sometimes will include hot gas bypass in addition to all this stuff, because at extreme low load conditions, it might prevent your compressor from tripping off. Different reps have different opinions on that and different experiences. I've done it like this before. and it seems to work real well as an extreme part load freeze protection, but it may or may not be needed. It really has to be looked at on an individual basis. Simultaneous heating and cooling is the auxiliary reheat. So if you have electric heat in this unit, you want it to be able to run at the same time as your compressors so that you can get a little bit of that extra reheat on those extremely rare cases where you don't have enough hot gas. It's a nice idea to have a variable speed supply fan. I'm a big fan of variable speed condenser head pressure control because the head pressure, the ability to control that consistently affects everything else in the refrigeration cycle, so that's nice. UV lights, we didn't talk about that too much, but some applications, UV lights are nice. And if your system requires final filtration, we have the ability to add final filter modules, HEPA filters, 2-inch, 4-inch, 6-inch, whatever you need to the discharge of the DX units. And I think that covers it. Oh, if you're going to put a filter module on the unit, you better make sure you have a high static fan, which most specialty equipment comes, pre-made with that. So that's kind of an overall view of all the features needed in a unit, in my opinion, in my experience, to meet the design objective. And I forgot to mention the application-specific controller, which just popped up here. So the controls ties all this stuff together. And again, the unit we just looked at will work very well in lab applications, pharmacies, archival storage, manufacturing, any facilities that require low temperature, low dew point, monitoring and control through all load conditions. Okay? All right. So that ends my presentation. Thank you very much. We appreciate everybody who stuck around here. If you have an application for us to look at, please reach out to your Insight Partners rep. If you're in another territory or don't know your rep, give us a holler. We'll connect you. Or look them up online. HVACwebinars.com. I think Chris is going to send out the link to that. And also, please connect with us on LinkedIn on our Insight Partners business page. And Chris is going to go ahead and chat that out in the chat. You can click on it